Hello student, good morning. I am Dr. K.Sinha, Professor of Chemistry. Today I will continue from the last class. Actually I am discussing gaseous states part 1, states of matter, and I am reviewing the entire chapters. After that I will discuss multiple choice of questions including numericals. Numericals may be hard and medium also, sometimes very hard. Then last class I have discussed postulates of kinetic theory of gases. Now I am going to discuss Maxwell distribution of velocities. Maxwell distribution of velocities. What is Maxwell distribution of velocities? Now I am telling you. It is a plot of fraction of molecules versus the corresponding velocities at a particular temperature. This is shown in the diagram. You can see the diagram along with temperature. Correct? Diagram, it is a Maxwell distribution of velocities at different temperature. It is shown in the diagram. Okay, there are different type of velocities. Correct? Then first velocity is most probable velocities. Second is root mean square velocities, also called RMS velocities. Third, average velocities. Correct? Then now in the diagram, by the seeing the diagram, you can understand these velocities. I told you that it is a plot of fraction of molecules versus the corresponding velocities at different temperature. Correct? Then in diagram you will see that at a temperature T1, at temperature T2, in two different temperature, you will see that this velocities, that is called molecular velocities. Then you will find at a T1 temperature, some molecules in the gas will have a special type of velocities, and when temperature will change, then that time it will have another type of velocities like alpha 1 and alpha 2. Then suppose at temperature T1, capital T1, velocity is alpha 1. Correct? Then that time when temperature was at T1, then that time what was the fraction of molecules? That fraction of molecules is called, actually you can tell, delta T upon N. Suppose number of molecules were in gas, capital N was the total number of molecules. Then all molecules will not have the same molecules. Different, all will not have the same velocities. Then some molecules out of N will have some special velocities, some fixed velocities, special velocities, one type of velocities. Then what is that number? Then suppose it is a delta n divided by n. That is called, you can say, this fraction of molecules. Fraction of molecules. Suppose 1000 was the total number of gaseous molecules. In that you are talking about 100 molecules were having one type of velocities. Then what is fraction? 100 divided by 1000. 100 you can consider as a delta n, total n. Then delta n divided by n, that is called fraction of molecules. Then if you will draw the graph, then the graph you will see that at the top, just like a barrier, barrier, velocity barrier, you can tell. Then at one temperature, that is at peak T1, what is the, you can say, fraction? Suppose it is a small T1, a small T1. At capital T1, that is a temperature. That time, what is the fraction? Then from that peak, just you parallel to the x-axis, just you wherever it is cutting the y-axis, that is the, you can say, fraction of molecules. Then at T1, what was the velocity? What was the velocity? Suppose it was the alpha 1 velocity. Now suppose you have changed the temperature. Now temperature became T2. And that time at the peak, what is the actually number of molecules? Then suppose that now it is at a T2, capital T2. That time a small T2 is there. That is a fraction of molecules. This may be, I can say, less. Suppose now here T2 is more than T1. T1 was less. Now suppose T2 is more. When T2 is more, temperature is more, then velocity will be more. And when temperature was less, then velocity was less. Means alpha 1 is less and alpha 2 is more velocities. Okay. Then these alpha 1 and alpha 2 velocities, alpha, that is called most probable velocities. Now by the graph, you have in the graph two peak you are seeing. One is at temperature T1 and other is at temperature T2. Okay. Now I am defining most probable velocities. What is the most probable velocities? By name itself is there, clear. Most probable. Possibility is more. Then most probable velocity, that is denoted by alpha. Then this is the velocity possessed by the maximum fraction of the molecules at a particular temperature. Then what is the most probable velocity? Then this is the velocity possessed by the maximum fraction of the molecules. Suppose out of 1,800 molecules, they have same type of molecules. Then that velocity is called, velocity which is possessed by the, you can say, maximum fraction of molecules. Then that velocity is called most probable velocities at that particular temperature. What is the root mean square velocity? RMS, that is denoted by U. Okay, UV, that U. Then RMS velocity, you can define it as, RMS means root mean square velocity. Then it is defined as the square root of the mean of the squares of the velocity of the molecules. By this heading only it is clear. Root mean square velocity. Mean squares means you can say squares of the velocity. Its mean means just like average. Mean, that is called root. Under root means squares of the mean. You can tell like this, under root, that is the square of the velocities divided by n number, a small n, that is called mean. Just like average, here you are doing average for square velocities. Suppose velocities where V1 molecules, V2, V3, V4, V5, ... Vn. Then V1 square plus V2 square plus V3 square plus V4 square ... Vn square divided by n. That is called RMS velocity. And RMS velocity, that is a U. is equal to under root v1 square plus v2 square plus v3 square plus dot 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 plus vn square divided by a small n, where n is the number of molecules. Okay. Different type of molecules which have different velocity. Suppose this one type of molecules are having v1 velocities, other molecules v2, other v3, like that way. Hence, how many molecules are there having different velocities? You divide it by n. v1 square plus v2 square plus v3 square plus dot 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 plus vn square divided by n. Now, what is the average velocity? V. Average velocity is denoted by V. Then by name it is clear. This that you are knowing. Without telling, you can understand. It is the average of the different velocities of the molecules. That is the V1 plus V2 plus V3 plus V4 dot 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 plus Vn divided by n. Difference is in average and RMS difference, that RMS was root under root and velocity was in a square velocity, their average. Now here only velocities without a square. No, without a square, without root mean. Simple. V1 plus V2 plus V3 plus V4 dot 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 plus Vn divided by n. Then three type of velocity I have discussed. Most probable velocities, root mean square velocities, and average velocities. Now question is asked, relationship between alpha, u and v. Relationship between all three velocities, most probable velocities, root mean square velocities, and average velocities. Then now I am telling you relation between most probable velocities and average velocities and RMS velocities, alpha, v and u. Then now alpha is actually formula I am telling you. One more formula is there. Okay. That expression I am telling you. Alpha means most probable velocity is equal to under root 2RT divided by m. 2RT divided by m, capital M, molecular mass. And V is equal to V, that is the average velocity, is equal to under root 8RT divided by pi m. Pi means 22 divided by 7. Then here in alpha, most probable velocity is 2RT divided by m is there. But here in average 4 times more means 8RT, and here pi m is there, and both are under root. And in case of u, that is the u means RMS. Remember, root mean square velocity is u, and u is equal to under root 3RT divided by m. Then you can see alpha and u. Alpha is 2RT divided under root 2RT divided by m. Here 3RT, same, under root 3RT divided by m. In the place of 2, write 3, that is the u. And average is 8RT divided by pi m. You remember, average is differing more, 8RT divided by pi m, but all three are under root. Question is asked, correct? You have to find out which one is alpha, which one is u, which one is v. Then now after putting, or you can say values, means all three how they are related, then I am telling you relation how v and u are related. How v and u are related. Then now I am telling you v means average velocity. V is equal to 0.921 u 0.921 into U. Correct? That is the relation between V and U. V is equal to 0.921 U. In the place of 0.921, if you write a complete 1, then both will be equal. Both will be equal. But here it is a less than 1. 0.921. 0.921 less than 1. Then V is equal to 0.921 U. And this is the relation between V and U. Now, alpha and U relation you can see. Alpha and U means most probable velocity and RMS. Then here again you will find alpha is equal to 0.816 U. See, it is more or less than 1. More or less than 1. 0.816. There V was 0.92. This was more than here. Here is 0.816. 0.816. Then alpha is equal to 0.816 U. And there V was 0.921 U. Then now see, V was related to U and alpha is related to U. Hence all three you can write alpha is to V is to U. All three. That is equal to 1 is to 1.128 is to 1.224. You remember, question is asked. Alpha is to V is to U is equal to 1 is to 1.128 is to 1.224. Means you can tell alpha is less than V. V is less than U. Means U is highest. U is highest. Then U means root mean square velocity is highest. And least is alpha. Most probable velocity is least. And in the middle, average velocity is there. Name itself is average. It is coming between the two. Remember that U is a highest among three. Now next point I am discussing kinetic gas equation. Kinetic gas equation is equal to what? PV is equal to 1 by 3 mn c square or u square you can tell. 1 by 3 mn u square. This is the expression for kinetic gas equation. Very, very common expression or equation. PV is equal to 1 upon 3 mn u square, where P is pressure of the gas, V is volume of the gas, and m is mass of each molecule. Mass of small m is equal to mass of each molecules, and small n is equal to total number of molecules, and u means RMS velocity. Hence PV is equal to 1/3 mn u square or c square also you can tell. C means here velocity or u means also velocity. Okay, both it is represented by both. Sometimes u, sometimes c. Both have same meaning. Then now PV is equal to 1 by 3 mn c square is very mn c square or mn u square. Anything you can tell. Then this is very, very, you can say, important relation. Now I am telling you relation between average kinetic energy and absolute temperature. This is again very, very important equation. Then relationship between average kinetic energy. What I told you expression, that expression and absolute temperature, how both are related. Because I told you with temperature, velocity change, that also you know, and energy energy also change. Then how How both are related, I am telling you. Pb is equal to 1 by 3 mnca square. That you can write m into n, a small m into a small n. In the place of that, you can write molecular mass. Capital M you can write. Because one molecule has mass small m, then n molecules how much? M into n, that is the molecular mass. Then 1 by 3 mn, in the place of mn you can write capital M, molecular mass. And let the U square same, means 1 upon 3 mu square. Now you can see 1 by 3 is there. Now just to multiply by 2 by 2. No change, 2 by 2, 2 will be cancelled, but you can write 2 by 2. Then that you can arrange like this. 2 by 3 into 1 by 2. Same things you can write like this. 2 by 3 into 1 by 2. Then 2 will cancel, it will remain only 1 by 3. But you can write like this. 2 by 3 into 1 by 2 mu square. Then now what is the mu square? That is the kinetic energy, half mv square. You know, kinetic energy is equal to half mv square. Then here half mu square means kinetic energy. Hence now you got new relation 2 by 3 into kinetic energy. See how both are related. Now you got Pv is equal to 2 by 3 kinetic energy. Then how you got these things? Then very simple way. Pv is equal to 1 by 3 mnu square. In the place of mn you have written capital M. Now it became 1 by 3 mu square. Now just you multiplied by 2 by 2. And then you have arranged 2 by 3 into 1 by 2 mu square. Then half mu square means kinetic energy. Hence you got 2 by 3 kinetic energy. That is equal to Pv. Then now if you want to, now you got Pv is equal to 2 by 3 kinetic energy. Then what is the kinetic energy? Then kinetic energy, that you can write 3 by 2 Pv. This way also you can write. Kinetic energy, Pv is equal to 2 by 3 kinetic energy. The kinetic energy is equal to what? 3 Pv by 2. Just simply by cross multiplication you got. Then now Pv is equal to what? Now you know. For 1 mole of gas, Pv is equal to RT, you know. Then in the place of Pv, you can write RT. For 1 mole of an ideal gas, Pv is equal to nRT is the gas equation, ideal gas equation. Hence in the place of Pv, you can write RT for 1 mole of an ideal gas. Hence kinetic energy, you can also write 3 by 2 RT for 1 mole of an ideal gas. Hence you can again further one more change you can write kinetic energy. Kinetic energy, now you have written 3 by 2 RT. But this RT is there. This is for, you can say, n molecules, capital N, Avogadro number. Actually, this we have written for 1 mole of an ideal gas. Kinetic energy is equal to 3 by 2 RT. That is for 1 mole. For 1 mole. Then, if we will divide it, for 1 mole means what? Avogadro number. Avogadro number of molecules. 1 mole means Avogadro number of molecules, means 6.02 into 10 to the power 23 molecules or particles. If you want to know only for 1 molecule, then you divide it by Avogadro number. That is the capital N, or A also you can write capital A. Okay. Then if you divide by Avogadro number, now here N, capital N is representing Avogadro number. Then you will get kinetic energy for 1 molecule. For 1 molecule. Then this actually for 1 kinetic energy for 1 molecule is called Boltzmann constant, kappa, just a small k. small k. Small k is equal to R upon N. You remember this for here kinetic energy you can also write that 3/2 because R divided by N, gas constant divided by N, that is actually Boltzmann constant. R divided by N, that is called Boltzmann constant. A small k, kappa like letter we can use. Then now kinetic energy you can write in the form of Boltzmann constant. Then the same relation, kinetic energy is equal to 3/2 RT was there. Now you divided by N. Then R upon N, that is called kappa, that is called Boltzmann constant. Hence kinetic energy is equal to 3/2 Boltzmann constant into T, kappa T you can tell, 3/2 KT, a small KT. Okay. Then here you remember a small k is equal to R upon N. Means for one molecule, value of R for one molecule of gas, that is called Boltzmann constant kappa. K is equal to R upon N. Now what is the difference between ideal gas and real gas? Now I am telling you. A gas which obeys Boyle's law, Charles' law, etc., or ideal gas equation. Correct? A gas which obeys Boyle's law, Charles' law, Avogadro's law, whatever is there, or you can tell ideal gas equation, that is the PV is equal to nRT under all condition of temperature and pressure, is called ideal gas. Again I am telling you, a gas which obeys Boyle's law, Charles' law, etc., or ideal gas equation PV is equal to nRT under all condition of temperature and pressure is called ideal gas. What is the real gas? A gas which obeys these laws only when temperature is high and pressure is low is called real gas. You remember, a gas which obeys these laws, means Boyle's law, Charles' law, or you can tell ideal gas. A gas which obeys these laws only special temperature, means high pressure and low pressure. High temperature, low pressure. A gas which obeys these laws only when temperature is high or pressure is low is called real gas. Now see what is actually meaning. High temperature. If temperature is high, then what? Molecules will move freely. Their speed will be more, velocities will be more. Correct? Free. It will become high temperature means movement velocities will be more. Actually, you have to increase the velocities. Then now, one condition, how will you increase the velocities? How will you make free? Then by increasing temperature, high temperature, velocities will be more. Free, they will move, they will feel free to move. And other condition, when pressure is low, if pressure will be high, more high, then they will come close, then they will not move freely. But if pressure is low, then again further it will move freely, fast. Actually, you want to make the gas fast. Then for that, two conditions you have applied. High temperature, that time it will, their energy will increase, velocities will increase. And second case, when pressure will be low, that time also velocities will increase. That's why high pressure and a low temperature is condition for real gas. A gas which obeys ideal gas, means Boyle's law, Charles' law, gas we will follow Boyle's law, Charles' law, Avogadro's law, then that gas, this ideal gas also, when you can say this real gas, when temperature will be high and pressure will be low, then real gas also behave like ideal gas. Okay, then a gas which obeys this law only when temperature is high or pressure is low is called real gas. Okay, real gas also behave like ideal gas. Only condition is of high temperature and low pressure. One more point I want to discuss, compressibility factor. What is the compressibility factor? Then very easy way you can get the expression very easy way, and you keep in mind very easily. You know PV is equal to nRT, that you know. Correct? This relation you keep in mind. The extent of deviation, I am telling the definition of compressibility factor. What is the compressibility? Compressibility factor. Compress. It came the word from compression. Compress. Compressibility factor. Now I am telling you the extent of deviation of real gas from an ideal behavior is expressed in terms of compressibility factor Z, capital Z, defined as Z is equal to PV upon nRT. Means ratio of both PV and nRT. Then what will remain? PV divided by nRT. That should be actually 1. Correct? 1. Only that time PV and PV divided by 2RT should be 1. But here you don't know, always it will be not 1. That will be that will have some value. That is called Z, capital Z. Correct? That Z is called compressibility factor. Then it is the ratio of PV divided by nRT, means PV, ratio of PV and nRT. What is the value? That is called Z, compressibility factor. Sometimes it will be equal to 1, and sometimes it will differ from 1. Okay. For ideal gas, Z is equal to 1. You remember, for ideal gas, Z is equal to 1, means PV is equal to nRT. Okay. At all temperature and pressure. For ideal gas, Z is equal to 1. For real gases, what is the value of Z? Now I am telling you. For real gases, greater is the departure in the value of Z from 1, greater is the deviation from ideal behavior. Okay. Greater the departure in the value of Z from 1, greater is the deviation from ideal behavior. When Z is less than 1, the gas is said to show negative deviation. Remember, less and negative. You keep in mind. When Z is less than 1, the gas is said to show negative deviation. This implies that the gas is more compressible. Means you can compress, you can press the gas more. Okay, this implies that if Z is less than 1, this is called negative deviation, and this implies that gas is more compressible than expected from ideal behavior. Means gas can be compressed more. And when Z is greater than 1, more than 1, the gas is said to be show positive deviation. Remember, more than 1, positive. If Z is equal to more than 1, then it is said to show positive deviation. This implies that gas is less compressible than expected from ideal behavior. Now example I am telling you. At ordinary temperature, H2 and helium, hydrogen gas and helium show positive deviation only, means Z is greater than 1 at ordinary temperature. At ordinary temperature, H2 and He means helium gas show positive deviations only. However, at low temperature, even these gases show negative deviation. Remember, at low temperature, hydrogen gas or helium gas. However, at low temperature, even these gases means hydrogen and helium show negative deviation, that is the Z is equal to less than 1. For example, in cases of these gases, if T is very less than 273 Kelvin, if T is very less than 273 Kelvin, Z is less than 1. Z is less than 1. Now I am stopping only here. Next class again I will continue. Thank you.